right, so in this lesson we are going to talk about how to solve exponential equations. And so one of the things that we have to be able to do to solve an exponential equation is undo the exponent, because that is where the variable that we're solving for is going to be located. And that variable can be x or whatever, it's not a big deal. Like here's one that's shown with t as the variable, which is common in context problems. But you'll notice that in an exponential equation, the variable is always part of the exponent. And it might be part of one exponent. It might be part of two exponents. This structure is kind of what we need, unless we have bases that are the same. We need two and only two powers or terms in our equation. And the structure that you see here, where you have a power on each side, and you might be thinking, well, what about the 6? 6 is a power because it has an exponent of 1. So in this type of equation, we think of it as a power of 6 to the first power. And so we need this in order to, the structure of a power equals a power, in order to undo the exponent correctly, or have a valid undoing with our algebra. And what we use to undo an exponent, because our exponent is a variable, is the inverse of an exponential function. So remember, exponential functions have the variable in the exponent, and their inverse is a logarithm function. Inverses undo one another. And so if we need to undo an exponential situation, meaning that our variable is in the exponent, we undo that with the inverse function, which will be a logarithm. And in undoing the exponent, we can use a logarithm of any base, but for context problems, when we need to evaluate, which we'll be practicing today too, get a decimal approximation for our logarithm expression, we often use either the common logarithm, base 10, or the natural logarithm, base e. And that is simply because our calculator is programmed to evaluate those into decimals for us. Before we had nice handheld calculators, there were books and books and books with tables and tables and tables of logarithm values that mathematicians and scientists would use to evaluate logarithms in their problem solving. So this outlines the procedure. So one of the things that is the first thing in this procedure is what I was referencing on the previous slide, that we may or may not have this structure when we are first given the equation, but we need to create this structure of a power equals a power. So one term equals one term in order to use this method. And then we will take the logarithm of both sides to undo our exponents, so that we can pull our exponents, our x's, out of the exponential position. We can use common or natural, and I'll talk about both for a while. I will say that for many problems, not all of them, the common logarithm is used, but for many problems the natural logarithm becomes the more used logarithm in these problems. So just so you know, you might want to just stick with the natural logarithm, because we can use the natural logarithm for all of these types of problems. Those with a base of e, which remember is your natural logarithm base, and those without a base of e. The common logarithm is not used with base e equations because it doesn't undo as nice and easily as a natural does. And we'll talk more about that as we get through it. But for the most part, I eventually start to use natural logarithm unless my base is 10, which matches the common logarithm base. Now, notice it says both sides. This is a common error. It's an algebraic procedure, so you've got to make sure that whatever you do to one side, you do to the other side. And so the logarithm has to be taken of both sides, no matter what's on each side. Then we will use one of our properties of logarithms that was introduced in the first lesson, and that is the power property of logarithms, which says, so now we'll have this structure on both sides of our equation in many cases. And so if we have this structure, we will undo this structure by using this power property of logarithms that says we can take this exponent and pull it to the front as a multiplier, and it creates an equivalent expression, so, which means that it looks different but has the same numeric value. So we turn it into this. Once we have this, which means x times log base b of a, then we can continue using our basic algebra, our undoing algebra, to solve that equation. And then we will, in this example or in this lesson, be giving both exact answers, which will involve our logarithms, as well as decimal approximations. So this down here, which says the property of equality for logarithms, this right here is what we're using. This property is what we're using for step 2. That's why it's here. When we say take the logarithm of both sides, what we have then is that positive numbers, if we have x equals y, then taking the logarithm of the same base of both sides creates an equivalent expression. So we're starting with this x equals y, this power equals a power structure. And then we're taking the logarithm of both sides, which gives us an equivalent expression, meaning that x and y would still have the same relationship. All right, so let's take a look at applying this procedure to an exponential equation. So we are to solve the equation. Notice it says we are to give the exact solution. That means no decimals, no calculators should be necessary. And we're to approximate that solution to 3 decimal places, which would be our nearest thousandths place. All right, so our first step is to create 2 terms, one on each side of the equal sign. That power equals a power structure. So I can do this in this equation because my 4 and my 7 are both rational numbers, so they're like terms, so I can add them together, undoing the subtraction, and so this now gives me 5 to the power of x equals 11. Once I have this power equals a power expression, now I move to step 2, which is to take the logarithm of both sides. And I can use either the common or the natural. And I'm going to do this one both ways. Okay? So what it will give us is 2 different forms of our exact solution, one involving a common logarithm, one involving a natural logarithm, but both of them will give us the same approximate solution, the same decimal value, and that's why we can use either logarithm. So using the common logarithm, I would have my common logarithm of 5 to the power of x equals the common logarithm of 11. Using my natural logarithm, I would simply use natural logarithm. Natural logarithm of 5 to the power of x equals the natural logarithm of 11. All right, so now I'm moving into my step 3. This is where we use the power property of logarithms. So when we have, remember, this structure. So we have a logarithm of a power, and that power involves our x. We're going to rewrite it as x becoming a multiplying factor. So this x moves to the front, and this becomes x times the log of 5 equals the log of 11. Over here, using our property, the x comes to the front as a multiplying factor, and over here we have x times the natural logarithm of 5 equals the natural logarithm of 11. All right, so now because we have now removed the variable from the exponent position, we can now use our basic undoing algebra. Undo addition, subtraction, undo multiplication, division, that kind of a thing. And so one of the things that I want to point out to everyone at this point is something that I often see that shows a lack of understanding of a logarithm. A logarithm and its argument can never be separated. Let me say that again. A logarithm and its argument can never be separated. So it's not like I can divide by 5 by itself, because the 5 is the argument. I also cannot divide by log by itself. That has no meaning whatsoever, and because it doesn't also have an argument. A logarithm means nothing without its argument. So I am undoing this multiplication by dividing by the log of 5. Remember what we learned about a logarithm? What does a logarithm represent? Remember, it represents an exponent value. And it doesn't represent an exponent unless it has all parts. The logarithm, the base, which is our 10, and its argument. Now this represents a number that is an exponent value. And so we do that on both sides. And that's going to now give us x equals the log of 11 divided by the log of 5. Remember that in our properties of logarithms, there is no property that allows us to combine these in any way. This is a division of two exponent values, and so we just leave it in this form. This right here would be our exact solution. This is our exact solution. Over here, I would undo this multiplication by dividing by the natural logarithm of 5 on both sides. And so now what I have is x equals the natural logarithm of 11 divided by the natural logarithm of 5. Also, no properties of logarithms that allow us to simplify that any further here or combine those into one logarithm. So here is an alternate exact solution. Both of them are considered equally correct. So now I'm going to go and I'm going to use my calculator to approximate these. And we should find out that they each give us the same decimal value. When you take your log of 11 divided by the log of 5, or your natural log, remember that in a calculator, arguments must be enclosed inside parentheses, must, which means that in the calculator, I would hit log and it would open a parenthesis. I must close that parenthesis after the 11 before I hit divide, close my argument for the 5, hit equals. If your calculator works backwards, then what you're going to do is literally do this backwards. 11, hit the log key, then hit divide, 5, log key equals. All right, let's see what we get. All right, so here, this one's a little interesting. So I just want to remind everybody about the rounding. In this case, I get 1.4898. So this is the spot, the 9 is where I want to round to, that third decimal place, the thousandths place. So the 8 is what tells me whether it goes up or stays the same. And so in this case, it will go up. Well, 9 then goes up to 10, so it carries over and also then changes the 8 before it to a 9. So this becomes x is about 1.490. And yes, we need the 0 because we are rounding to that third decimal place. Now, if we've done our math right in both of these, the natural logarithm expression should give us exactly the same decimal value. And calculator usage would work the same as what I showed over here with the common logarithm. You just use your ln key. So, and we see we get exactly the same decimal, which is going to round exactly the same way. So these are what we would consider the approximate solutions. These are the exact solution. Like so. So learning how to interpret structure, and how to undo that structure correctly is important. It requires a knowledge and understanding of order of operations. And so here, when we look at this particular exponential equation, we have to understand that over here on the left side, the 3x plus 2, of course, is our exponent, and we need to correctly identify the base of that exponent and understand that the base is the 7, and that cannot be changed. So like some people will mistakenly multiply 2 times 7 to change the base to a 14. That's incorrect. It's invalid. And it violates order of operations, because when you're doing calculations, when you're doing simplifying, exponents have to be simplified before multiplication can be done. We can't simplify the exponent. There's no way for us to simplify or change into a number 7 to the power of 3x plus 2. Therefore, we cannot do the multiplication between 2 and the power. So instead, what we have to do is create that structure of a power equals a power by undoing the multiplication between the 2 and 7 to the power of 3x plus 2. So we would begin by dividing both sides by 2. So now we have is 7 to the power of 3x plus 2 equals 250. This is a power equals a power structure. Again, 250 is considered a power because it has an exponent of 1 in this situation. So now we undo that exponent using the inverse function of logarithms. Here I'm going to use the natural logarithm instead of doing both, and again, it's your choice. Sometimes I'll pick one over the other, and the only reason that I am choosing to use natural here is simply because it's more often used in calculus. Since that's what we're preparing to be ready for, I'll use natural logarithm here. So I'm going to take the natural logarithm. Again, it has to be of both sides because it's an algebraic procedure. It's sort of like squaring both sides or dividing both sides by our 2's we did above. Now we're going to undo our exponent using that power property of logarithms. Here's where this problem is a little bit different than the previous problem. So one difference was understanding how to begin through undoing multiplication with division. The second is the structure of our exponent includes addition. Here, our structure of our exponent, it was just the variable of x, a very simple exponent expression. This involves both addition and multiplication, a more complex structure. So we have to realize that when we pull this to the front as a multiplying factor, that entire quantity is going to be multiplied times the natural logarithm of 7. Remember, the natural logarithm of 7 is an exponent value, so it's a number. So this is actually the same structure as if we had like 3x plus 2 times, let's say, 4. We are going to distribute this number to what is in the parentheses. That's how we would multiply this sum times the outside number. So we're now going to distribute our natural logarithm of 7 to the 3x and to the 2. Now, when you write this, structure is important. All right, this is a little bit different than how we've written things, but it does match the structure that we have seen in other situations with our logarithm functions. So whatever is inside parentheses should be in front of the natural logarithm of 7, so that we maintain that our argument is 7 and don't actually think that we're multiplying this argument of 7 times anything here in our parentheses. We're not. That argument cannot change. So we have 3x times the natural logarithm of 7 plus 2 times the natural logarithm of 7 equals our natural logarithm of 250. So now remember what our goal is. We're solving for x. So now we are getting into our undoing algebra, where we are going to get x by itself. So remember, reverse order of operations. So the first thing I'm going to undo is this addition. So I subtract 2 times the natural logarithm of 7. This is the same thing as if I wanted to undo a plus 2x. I would subtract 2x from both sides. Same structure. It's just instead of an x, I have the natural logarithm of 7, which represents some exponent value. Guess I didn't want to erase that part. Now, I'm writing this over to the side to make it very clear that I cannot subtract the 7 from the 250. There's no way I can combine these two through subtraction. I could use the quotient property of logarithms, which we learned about in the first lesson, but it's unnecessary here. If you wanted to do that, you can, but it's not required. You'd first have to undo the 2 using the power property, and then you could, which would make this the natural logarithm of 49, and then you could use the quotient property, which would make this the natural logarithm of 250 divided by or over 49. So it's okay to do that, but it's not necessary. So now we have is 3x, and I'm going to keep that dot there to help us remember that's multiplication, but it's not required. And I'm just going to write this as subtraction over here. So now, here I have to realize to get at my x by itself, I want this to be as clean looking of an exact solution as possible. So think of this, guys. This is all multiplication. This is 3x means 3 times x. So I have 3 times x times the natural logarithm of 7. It's like if I had 2 times 3 times 5. I have 3 factors. I can write them in any order I want to. So think of this as x times 3 times the natural logarithm of 7. Think of it that way. Because what we're going to do is undo this multiplication. So we're not going to divide twice. We're not going to undo multiplication twice. Once for the natural logarithm of 7 and once for 3. We're going to undo one multiplication with one division of this product. So now 3 divided by 3 is 1. Natural logarithm of 7 divided by itself is 1. X times 1 is x. And then what I have over here is this rather messy looking solution. So this is our exact solution. The solution before we use our calculator. All right, so now I'm going to use my calculator. Again, arguments have to be enclosed in parentheses. And here's the other thing you need to remember. Order of operations. If you're going to do an expression in which you need to do something in your order of operations that normally isn't done first, then you have to enclose it in parentheses. For example, if I have 10 minus 2 divided by 4, I need to make sure that this subtraction between the 10 and the 2 is done before the division. So my calculator, if I just type 10 minus 2 divided by 4 into my calculator thinks that I want it to do the division first, and I don't. So the only way I can get my calculator to change that is by putting parentheses around the subtraction. So that is also something that I have to do in this logarithm expression. So I am going to need parentheses around this logarithm expression, and I'm going to need parentheses, let me change that to a different color, around each of the arguments. So notice here at the end you'll have a double close. Without that double close, you will not get the correct decimal value. So here's the other tricky thing. So now the structure of this denominator. This is multiplication. I actually need the calculator to do this multiplication before it divides. So let's go over here to my number example, my simpler situation. Let's say I have this is times 2. So if I just type times this expression here, 10 minus 2 divided by 4 times 2 into my calculator, it will do the division, then it will do the multiplication, and then it'll go back and do the subtraction, because order of operation says to multiply or divide left to right first, then add subtract left to right last. So if I want to change that and make it do this multiplication first, I need parentheses here, and I need parentheses here to get it to do that subtraction. I want it to do that division last. So I have to have this structure in my calculator. So the same thing is true over here. I am also going to need to have parentheses around that product in my denominator. So now what my calculator sees is, okay, I do this subtraction, then I do this multiplication, and then I'm going to do that division between those two final numbers last. All right, let's see what we get. And I also didn't mention, but this is another argument, so there should be parentheses around that argument. So you've got another double close there. That one at the end isn't as important as the one up above. All right, so to 3 decimal places. So we're looking at 2791, and the 1 tells us the 9 stays a 9. So we have 0.279 as our approximate solution. All right, so in this final example, we are looking at an exponential equation where we have the variable of x in both exponent positions. So our first 2 examples only had a single x in one exponent. So here we're going to talk about what our algebra needs to be in order to get our x's together so that we can have an x equals a number solution, which is the only type of valid solution. So some people will mistakenly have like x equals log 3 minus x log 2. You can't have a solution for x with an x on the other side. That's a big no-no, okay? So here we would start the same. I have a power equals a power structure. So pretty much, you know, like this is my step 1. It's given to me that way. So now I decide which logarithm I want to use to undo those exponents, common or natural. Again, I'll use natural just because that's the more often one used in calculus. So I have the natural logarithm of 3 to the x minus 5 power equals the natural logarithm of 13 to the power of x. So now we're going to undo those exponents using the power property of logarithms. And this time we have to undo both of them since they both involve x. The first one involves subtraction. So anytime your argument involves addition or subtraction, it's like a quantity that's being distributed to the logarithm. So it must be in parentheses. So these are required parentheses here around addition and subtraction. And then over here we don't need parentheses since we have a monomial exponent this time. No addition, no subtraction. So now I'm going to remove my parentheses by distributing my logarithm to the x minus 5. So I now have x times the natural logarithm of 3 minus 5 times the natural logarithm of 3. Okay, so now this is similar to what we would do. We have two terms that involve x, this one and this one. So this is similar to what we would do if we had like 3x minus 7 equals x. We would use our algebra to get our x's on one side, our x terms on one side, and our number terms on the other. And it does not really matter which we do. Our options, we could subtract 3x, and that would give us negative 7 equals, in this case, negative 2x, although with our logarithms we won't be able to combine them. Or we can instead subtract x and add 7. And it just sort of depends on whether or not we want to deal with a bunch of negatives or not. I personally don't like to deal with a bunch of negatives because I might accidentally lose one of them, and so I tend to prefer to do algebra that creates a positive quantity when I can, which would be this algebra. So I'll just demonstrate using this algebra, all right? Fewer negatives algebra. So what I'm going to do then is I'm going to, these lines now look like division. This is not division. So I'm going to undo this by subtracting it from both sides. And I'm going to undo the subtraction by adding this term to both sides. So this now is gone, this is gone. So over here on this side, I have 5 times the natural logarithm of 3. Over here on the left side, I have to realize these are different arguments. One has an argument of 3, one has an argument of 13, which means they are unlike terms. Unlike terms cannot be combined. Different arguments makes them unlike terms. So I have to leave this as a difference. No choice. Like so. So remember what I said about us needing a solution that's x equals a number, no x's on the other side. So here's where we have to use a more advanced strategy, and we use this strategy anytime we have multiple terms involving x that we cannot combine, that are unlike terms. So again, we're going to use this strategy anytime we have x terms that are unlike terms. What we simply do is say, fine then, if we cannot combine them together, well, x is a common factor, so let's factor the x out. So we're going to factor out x. And that gives us x times, in parentheses, the natural logarithm of 3 minus the natural logarithm of 13. And now we have a single x, and our algebra says, all right, well, to get this x by itself, we now need to undo this multiplication. So we're going to divide both sides by the quantity in parentheses. And I'm leaving these parentheses here for emphasis because we're going to need them when we do the calculation with the calculator. They're not absolutely required for the exact solution. So x equals 5 times the natural logarithm of 3, all divided by the natural logarithm of 3 minus the natural logarithm of 13. This is our exact solution. Okay, so now let's do the approximation. So, analyzing this as far as order of operations, we are going to need the calculator to do this subtraction before it does the division. We also need it to do this multiplication here before it does this division. So it'd be like, well, what if I had like 5 times 7 over, oh, I don't know, 6 minus 4. Where would I need parentheses in my calculator? Well, what would I be doing if I did it by hand? Well, if I did it by hand, I would do my multiplication and my subtraction first. So if I typed into my calculator simply 5 times 7 divided by 6 minus 4, my calculator would start with multiplication division from left to right. So it would do the multiplication, then it would do the division, and then it would do the subtraction at the end. That won't work here. I needed to do that subtraction before the division. But doing this multiplication first is fine. So I really don't need parentheses around the 5 times 7. But I do need parentheses around my subtraction. So now when the calculator sees this structure, it says, okay, start going left to right. Oh, wait, I can't do that division because of those parentheses. I better do that subtraction. Now I can go back and do 35 divided by 2 as the final answer. So now that means that you can put parentheses around this, but they're not absolutely required. Where they are required, remember, is around the argument of 3. So if you also decide to put parentheses here, you're going to need double parentheses. In your denominator, required parentheses around the difference, and required parentheses around each argument. That's what we're looking at. All right, let's see what we get. Okay, so here we have negative 3.7461. So that 1 tells us the 6 will remain a 6 this time. And here is our approximate solution. And remember, x started out in the exponent position. And so the exponent can be any real number. Again, an exponent can be any real number. Rational, irrational, positive, negative, or 0. Any real number. So this is perfectly valid for an exponent solution. All right, well, this is our final example for this particular lesson, and you should now have everything that you need in order to complete the assignment.